I'm really happy to invite Cyprien. Where is it? Oh, here. Okay. Cyprien is getting his mic on. So Cyprien is a researcher with three of my labs and also with dWallet labs working on integrating MPC within the consensus of the dWallet network. I think you're in for a really interesting presentation, and thank you, Cyprien. This is the clicker?
Yes.
Yeah.
Yes.
Yeah. I'll just speak loudly. Okay. So right now I'm feeling a lot like I did in my second year of my PhD, which is you come to a meeting with Nigel, your advisor, and you're really prepared to give, the thing you prepared, and then he just like does his Nigel thing, and then you're like, what was I supposed to say again? But okay, let's give it a try. So today I'm speaking about the project we've been working on with dWallet Labs for MPC on the blockchain. And I'll preface by saying I don't totally disagree with Nigel that doing general MPC over a blockchain isn't perhaps the smartest idea. But the really cool thing about this project is that we're not doing generic MPC, we're trying to do one specific kind of MPC. And in this case it works, and there's a lot of interesting questions to solve, right? Because MPC is this like advanced, complicated cryptographic protocol that makes a lot of assumptions on like how do parties actually talk to each other, and also how do you actually coordinate the execution of MPC, what happens when somebody like misbehaves, and all these kind of things. And blockchain is also like a cool, interesting, advanced cryptographic thing that is able to guarantee a lot of interesting security properties. So how do you connect the dots between those two things? And I want to give you guys a bit of an overview and an idea of the things we've been thinking about. And then, there's a paper that I'll point you guys to and stuff like this if you want to know more. So the outline is going to be a little bit about what it is we're doing, why we're doing it, kind of merged together actually. I don't know whether they're two separate points. And then most of the talk is going to be about how we're doing this. So what and why? Specifically, we want to look at ECDSA signatures, right? Because in the Web3 world, ECDSA signatures, they're essentially your identity. If you control an ECDSA key pair, you own things in the internet. You are someone on those different Web3 things. So the idea is to take those and then create a blockchain that kind of allows you to have more security and more functionality with that key pair. So to understand a little bit, we can take a quick look at how key generation works. Mathematically, that's quite simple. You take a random number x and then you compute an elliptic point curve. Signature is a little bit more complicated, but you have a nonce, and then you kind of take that nonce, multiply with your secret key, h is the hash of the message, and that's it, you've got a signature. So in terms of MPC computation, if we want to think about how are we going to do this on MPC, that's not a huge program. We're not talking about trying to execute millions of gates, right? We just want to do this. So that's already an advantage that we have. The thing is, of course, if you have a single secret, if you just own your own secret key for your ECDSA key pair, that's a single point of failure. If your device gets compromised, if your hardware token gets stolen or whatever, that's it. Someone else is you on the internet, and they can own what you own. So the idea is that, well, rather than just have one secret, split it into two, and then that makes it twice as hard to steal. The other cool thing is also, once you've split your secret into two, both halves are necessary to produce a signature, so you can start thinking about access control. Because just owning one half doesn't enable you to create a signature on your own. You need the other party to kind of agree to that. So you can start maybe thinking about access policies and things like this. So mathematically it gets a little bit more complicated. You got to split your nonce, you got to split your secret key. So there's the distributed secret key. And so the MPC protocols becomes a bit more complicated, but it's still manageable. Then we want to look at decentralized two-party ECDSA. Because the usual two-party setting is you have a client and you have a server. So I can have my client share, the server has their server share, and we can engage in assigning protocol with each other. But I can also like delegate my client share to someone else, my employee, if we have like a company wallet. And I can tell the server, okay, if someone with this token like uses their share to create a signature, as long as they're not spending more than like 10,000 euros a week, you can let them do that. But if they're starting to overspend, like they need my signature as well to do this. So you can think about slightly more complicated access policies for the same ECDSA key pair. The thing is, as I get the feeling, we don't really like centralized things, so we want to decentralize the server. We don't want there to be a single point of censorship, for example, if the server decides they don't agree to follow the access policy. Well, we want to avoid that. Also, if the server goes down for some reason or is unreachable, then we can't sign. So we're left, as they say in New Zealand, up the creek without a paddle. Of course, we want some kind of layer of public verifiability to check that everything's happening as it should, access policies are being respected. So we need two things to kind of realize this. We need an MPC protocol to actually handle the server's role. So the server's role in the two-party computation, we want to split that in an MPC protocol, because if you have kind of a big network of nodes who perform the server's roles, then you can't have censorship and you can't have like downtime if your network is still alive. And we also need a blockchain for the kind of the coordination and the kind of censorship resistance, arbitrary access policies, expressivity, and things like this. So I'm not going to speak specifically about the MPC protocol because that was already spoken about in the last Encrypt event by the dWallet team. That's a really cool protocol they put together to do this. I'm rather going to talk a bit more on how do we put this on the blockchain. So the first thing we look at is the MPC communication model. If you want efficient and secure MPC protocols, one of the really good communication models for this is Byzantine reliable broadcast, which means it's a broadcast channel that even if you have a certain proportion of malicious actors, if as an honest party you're sending a message into the channel, you're convinced it's going to pop out of the channel everywhere else. So all the recipients are going to receive the same message that you sent, and nobody's going to stand in the way of that. And also, if you have a publicly verifiable broadcast channel, then you can have publicly verifiable MPC, for example, if you have a transparent setup in your MPC protocol. So I want to take a little trip down literature lane and explain how do we achieve Byzantine reliable broadcast. So we start with Byzantine consistent broadcast, which is just slightly it's not less secure. It has slightly less functionality. So Byzantine consistent broadcast ensures that everybody who delivers something delivers the same thing. Not everyone might deliver a message, but at least if they do, they will deliver the same thing. So the way it works, one of the nodes, I've singled it out by calling him A, would broadcast their message. So this is kind of peer-to-peer channels. And they say, hey, I'm sending this message M into the broadcast channel. Everybody is going to reply with a signature, and they're going to echo the message saying, I agree, I've witnessed that you're trying to send M inside this broadcast channel. And then the sender node is going to then gather all of these signatures. That's why we now have like a capital sigma in the message, and they say, hey, look, I've gathered a quorum of signatures on my message. Enough people in the network are agreeing that I'm sending this through the broadcast channel. And then once you have this, all of the nodes can agree that, okay, this message M was sent through the channel and they can deliver it to their application layer, which in our case is going to be the MPC protocol. The thing is, that's only consistent broadcast. It's not quite secure enough because reliable broadcast, you want to make sure that everybody will eventually deliver. So you want to make sure that nobody delivers until everybody's ready to deliver, so that it can kind of all happen at the same time and at every node at the same moment. So instead of sending a final message in step 3, the node A will instead send what's called like an aggregated echo message, where it's still a collection, a quorum of signatures like this, and they say a quorum of nodes have witnessed my message. then they're all sending to each other like, okay, so for example, B1 says, I have witnessed the quorum of signature and I am ready to deliver the message. But they don't deliver it just yet. So they send this all over the network to each other. And then once a node has seen again a quorum of ready messages, then they deliver. So there's this kind of like, everybody agrees that someone's trying to send M. Everybody agrees that someone is trying to send M. And then you actually can say M has been sent in a Byzantine reliable broadcast way. So that's kind of what the literature tells us you need for reliable broadcast. And so if you have an MPC protocol that just says, you know, step 1, party A broadcasts something, well, that's fine in an MPC paper. Everybody's like, yeah, sure, you broadcast. But in practice, you actually got to make sure that these assumptions are realized by your communication channel. So what we decided to look at is one of these DAG-based blockchains. So specifically, we took a look at the Narwhal protocol. And so a DAG stands for a directed acyclic graph. And the idea is that at every moment in time, each validator kind of proposes a block. So that's why you have all of these rows. Every validator's propose blocks. And when they propose blocks, they kind of link them backwards to the previous blocks that were sent in the history. So you end up with this kind of thing that progresses forward, and it's not really a linear blockchain. You might think like Bitcoin, where it's just one block after the other, and then you need to wait for like a miner to pop up to say, hey, I've got the next one. Here, you know, you move through time, and you've got this kind of big graph of block that builds up. So if we look at how you build a Narwhal block, the validator who's trying to send it creates this kind of thing full of batches, like full of transaction batches, but these could be like MPC messages they're trying to send. This is basically just your payload. And then they sign it to say, hey, like this is coming from me. And then the Narwhal protocol says, okay, well, they should send this block to every other validator. That's kind of like the send message in the broadcast protocol. And then they collect a quorum of signatures from the other validators to create what's called a certificate. So here you've got the first two steps of broadcast. And the certificate actually, the certificate you can already send back to all the other validators, and in this case you would achieve Byzantine consistent broadcast because they could just all kind of deliver. And in some sense that is what happens in the Narwhal protocol. Once you've gathered your certificate, you send it out, and everybody says, okay, I now have a block from this validator at this round. And everybody agrees that this block exists and is available. But that's not the only thing that the blockchain has. It has, on top of this, it has the Bullshark protocol. So the Bullshark protocol, you can consider it's a consensus mechanism, which essentially linearizes the graph. So it says, like, okay, we have this graph, but at certain moments in time, you have these darker nodes. I know I gave Nigel some shade about the colors. I hope you guys can see the difference. So you have these darker nodes that are kind of like selected by the protocol by saying, okay, you are now like a key moment in the history of things, and we can linearize whatever comes before it. So you see dark blue gets linearized, dark blue gets saved, and then the light blue gets added. Then you can save red and then like linearize red behind it, and so on. So now you actually get ordering between the blocks and the linear history in the blockchain, which is when you are actually wanting to do transactions, finance, and stuff like this. It's super important to know what happens before what. So in this case, that's crucial. But if you remember, Narwhal only gives us consistent broadcasts, so we still need a little bit more from our protocol. And if we look at how Bullshark makes a decision to save a block, you can see this yellow block here. So it's in the graph, it's being broadcast. And then we look at the green one that follows. So when the validator 2 here is building the green block, so they're kind of send an echo for green, that's how they're building it. But because green points to yellow, it's also acting as an echo message. It's also acting as a ready message. It says the person who is proposing green knows that yellow exists. And so once they finish making their green block, well, other validators in the network will be making similar blocks, all pointing back to yellow. So eventually, at the round after yellow, you collect enough ready messages that point back, and you can say, okay, we're now ready to deliver yellow and consider it reliably broadcast as part of our history. So together, the Narwhal and the Bullshark protocols kind of combine to give you exactly this broadcast channel that MPC relies on for its efficient protocols. So that's the first part. It's kind of providing the underlayer of the MPC. But the thing is, MPC, like Nigel says, you can, once you're set up with your inputs and stuff like this, and you've got your participants, you can do your thing. But you need to get to that point. So you actually need a layer above the MPC that's controlling and coordinating how everything is taking place. And you can kind of split the requirements from this upper layer into several categories. So first you've got functional requirements. So, because in our case, the MPC participants are going to be the validators of the kind of the DAG-based blockchains. So you need, first of all, a signal for them to actually start their MPC. Well, this could be a user posting the transaction to the blockchain. So in the specific case of ECDSA signatures, the first step you want to do is actually create a key pair, right? So if you take dWallet's two-party MPC protocol, there's a keygen protocol where the user has to, they have to sample their share of the secret key, compute a public commitment to it, and then they have to send that to the other party. Well, that's the kind of the transaction they would do. They would post a transaction on the blockchain saying, I want to do key generation, here is my message, and because MPC says that it's private, this message doesn't actually reveal the key share of the user, but like this. And because you've got a linear history provided by the blockchain, everybody sees this, and the validators are saying, okay, we have now received the signal to begin our MPC protocol and exchange over the broadcast channel to do it. You also need agreement on which MPC protocols should be worked on, because the idea of this system is not just that one user has their wallet, but you have thousands, hundreds of thousands of users all kind of using the kind of distributed wallet. So you get to some point where there's all kinds of MPC requests being posted. Sorry, the laser is not the big green button at the top, which is kind of counterintuitive. So you can have hundreds of thousands of users posting requests. So blockchain actually gives you orders. You know which ones came first. There could be some kind of priority based on the kind of MPC you're requesting. There could be some kind of fee-based priority as well. You can kind of do a lot. Also, the user needs to receive the output of the MPC, right? So the end goal of this is that when the user requests a signature protocol, all the validators produce a signature using the ECDSA secret key that's split between the user and the blockchain. So they put that on the blockchain as well, and shortly after, any kind of block explorer would kind of give the user the signature that was produced. And because it's an ECDSA signature, they can take that to Bitcoin, they can take that to Ethereum, to wherever they need it to be posted to authorize anything. So these are kind of the functional requirements. The system actually helps you do something practical. You also need security requirements. So MPC protocols can abort, right? If one of the validators misbehaves or even just drops out, maybe you need to restart. So having a publicly visible record of the communication channel, that gives clear signals about whether an MPC protocol has succeeded or failed, and it gives the signal for it to restart so that the user doesn't actually have to repost or re-request anything. The blockchain should be able to iterate and try until it successfully completes. Of course, you need to exclude malicious validators because if someone can, on purpose, trigger an abort or a crash of a particular instance, then they could just do that forever, and then you wouldn't have any service provided. So the thing is, we actually need much stronger property from the MPC protocol, which is identifiable abort. If somebody messes up, we need to blame them and know who they are, so that the first thing we can do is actually just ignore them when we retry. So they can try and send a message, but we just say, sorry, you were malicious in the previous execution. We know because your zero knowledge proof failed or something. So we're not letting you on board, which also therefore means that you need to have a good balance of like the threshold required for the MPC to function and like the number of malicious validators that can be tolerated by the blockchain. Also, just excluding malicious validators, they might still want to kind of like selectively once in a while, decide to crash a signature they don't agree with. So we actually need to bring in another aspect of blockchains, which is financial incentives. That's something this MPC literature is completely agnostic about, but it's a huge part of blockchain and tokenomics research. And there's a lot of security that comes from the game theoretic aspects of tokenomics. So if we say, first we can say, people who do good work get rewards. So if you're identified as malicious and prevented from participating, well, there's your earning potential gone. And then the thing is, because we're basing this on like a delegated proof of stake mechanism, the moment you stop earning rewards, it's not your own stake you're not capitalizing on, it's everybody who delegated their stake to you in the hope that you would earn the rewards. So the moment you stop earning them rewards, they just take their stake away, put it with another validator who's doing a good job, and then the malicious validator is kind of booted out of the set of validators just by the kind of the tokenomics incentives. And finally, we also need some kind of like liveness requirements, because MPC does require kind of synchrony, people to, or like in some of the protocols that we have, you need you need the same set of party to kind of stay, to kind of be alive for the first few rounds of MPC. So we also have mechanisms where like, if someone is too slow to join, we're just not going to wait. As soon as we have enough validators that kind of signed up to do an MPC instance, the protocol says, okay, we're good, we move on, because we can now function. But we also require fast participation. We don't want people to just dawdle and say, I don't know, maybe I will, maybe I won't. So actually we base the reward mechanism based on the number of protocols that a validator leads to completion. So if you're too slow to join, that means you're not going to get any rewards from the execution of that instance. So you incentivize people to join quickly. And we also need to think about some of the MPC protocols. So I talked about key generation, signature. There's also like an optimizing protocol where you can do pre-sign, so you can do some of the heavy load of the signature computation without knowing what the message is yet. So the user can request these, stash them for a little while, and then as soon as they want to do a quick transaction, the network is very fast to respond with a signature. And so this, again, we can incentivize in the kind of the distribution of the rewards, making sure people don't shy away from doing the longer work that requires staying online for several rounds, and this kind of thing. So these are all things that kind of help coordinate the execution of the MPC and also incentivize proper behavior in the parties. This kind of thing Nigel was talking about a little bit about deciding who's going to participate in these kind of things. The blockchain is also very good at providing the properties that we require for this. I'll take any questions if you have any.
Did you make it dynamic that people can join and leave the network?
Yeah, so the blockchain has a concept of like epoch, and the idea is at the end of every epoch, validators can sign on or sign off, and then that's possible because there is like a homomorphic encryption. There's like a public key to the blockchain itself. It has a public key because that's how it keeps the shares of individual wallets, because otherwise you would have a huge bloat. Like if every validator needed to keep one share for every wallet on the network, that would be a huge storage bloat. So what you do is you can encrypt the share onto the blockchain under the common public key, and then each validator just has a piece of the blockchain decryption key. So when you have validator churn, you need a resharing. So you need to take that secret key, reshare it from the old set to the new set. Essentially.
This is automatic.
It's part of the epoch change. It's like an extra MPC protocol that happens just at every epoch boundary. And yeah, it kind of passes the baton to the next node. Yeah.
How does the protocol define malicious validator and slow one?
So how does it define a malicious validator? There's some very clear scenarios of being malicious, which is it's if you send like an invalid proof, everybody can agree. There is a concept of, you can say, if you cause a, like, so if you start a protocol which is now therefore reliant on you being alive, but you go down in the middle because of a network failure or something like this, that can be considered malicious behavior, because as a validator who's promised to be a validator, you shouldn't go down in the middle of a protocol. Slow is a bit trickier. So again, the kind of the Bullshark linearization kind of provides us with a bit of a clock. You know, it says, okay, now we have the blue moment and we have the red moment, and then you can say, okay, if you take 3 moments to reply, then you're not being as good as everyone else. But this is usually a bit more of a subjective measure. If you say, okay, if 70% of validators spoke within 2 moments, then they're okay. The ones that take longer, they're slow. But then it could be that there's congestion, and then you only get 70% after 5 blocks. Yeah. It's a bit of a flexible thing. Yeah.
I have 2 questions.
Mm-hmm.
The first one is that I just want to make sure I understand correctly. Is this observation correct that your MPC protocol is as fast as your communicating blockchain?
As in its speed is limited by the blockchain? Yes. The MPC protocol is throttled by how quickly you can have reliable broadcast from the blockchain. Yeah.
Second question is that how do you identify malicious validators? I'm not sure I understood that. Do you benefit from blockchain or you use classical techniques?
So you need classical techniques from MPC of identifiable abort. But if you have an MPC protocol with identifiable abort over broadcast, essentially anybody can read the transcript from the broadcast channel, and then you have identifiable abort visible to everybody. So the idea is that you have the identifiable mechanism, but it shouldn't rely on knowledge that is secret within the MPC protocol. So for example, it's the way it works at the moment, we're hoping to optimize it, is you, at some points you have everybody generates a zero knowledge proof. And if one of them fails, then it's like one of them doesn't verify, that's malicious behavior. It means they don't know the plain text that they claim to know or something like this. For optimization, you can aggregate them. So you aggregate the n proofs and then you verify that aggregated proof. So you don't have to do n times the work. But if the aggregated proof fails, then you have to, the identifiable abort mechanism says you unaggregate it and then you check each individually to see who's to blame for the malicious proof. Yeah.
I have another question. Is it possible to say that your protocol is publicly verifiable or not?
I think so.
Yes.
Yes, they say yes. Trust them.
It's a feature, so
Yeah. Thank you.